Hey guys, it's Tom Cherryholmes with the FujiNet project, and I wanted to give a status report and show some of the things that I'm running into here when working through how to interact with character devices on the AdamNet. This is rather important because the character devices will not only make up devices like the Wi-Fi modem, but they will also make up the FujiNet control device, which is what the configuration program will be interacting with to mount and unmount devices, set up network parameters, etc. The issue that I'm running into now is essentially dealing with long-running input and output devices and timing everything out so that it works correctly. So in order to facilitate showing where I'm at and everything, I'm going to take you through showing an example test harness, which is essentially a Telnet program, and how that Telnet program works before we dive into the firmware on the back end of it all. So without any further ado, we'll go ahead and go full screen on my Atom here. And we will go, I've already loaded the test program from the FujiNet itself, and this is actually using the EOS console routines. So it's pretty fast. We'll go ahead and log in here, use the default port, and you're going to see some things happening here. You may see pauses in the stream and whatnot, and you may see other strange things happen. But like I said, this is just because we're working through all of this. We connect, and we can see that it's streaming the data across. And you can see it stopped right here because it didn't send over the very last packet of information. I'm still trying to figure out why that's the case. We'll go ahead and set 32 by 24. Yeah, definitely some odd timing issues that I still have to work out here. But you can see it mostly works. And we may be frozen here. But I mean, this kind of gives you an idea of where things are at the moment. So with that, we'll take and zoom into the firmware itself. We'll start by basically looking at the Atom side of things. And we have right here a test terminal program using the Z88DK's ANSI console. And you'll see, yes, my network information is hard-coded in here. Big whoop, like anybody's going to try to connect. Okay, so some basic variables to do things like hold the host name that we input, the port, and what we have right here is a response buffer, and this basically holds the data that's received from the AdamNet. In this case, the data that comes in over the remote TCP socket. Since the maximum message size is 1024 bytes, I've created an array here that will hold that maximum message size. And each time that I do the receive request, I use the maximum message size so that the EOS routines will properly form the receive message and deem it as valid because those have to match. Some routines here from EOSLib. EOSLib is a library that I put together that wraps all of the various EOS functions to do everything. Basically, all of the functions that are defined in EOS have C equivalents in here, and in this case, I'm using them to set up the video system, everything like I want it to, and then finally set up the EOS console so I can use it. Since the EOS console routines don't have anything to display a single string, you have to display each character individually. I wrote a quick routine to take and do string displays. Very simple and to the point. Conversely, since since I can only read individual characters, I wrote a quick and dirty routine to grab character strings so that I can do the initial prompt at the beginning of the program. So with that, if we actually take and go and look at this from main, we'll see that we call our EOS console start, and we go ahead and we find the device command block here for the network device. Now the network device is actually device E. If we take a look right here, we can see this is the test network device that I put together. That's a character device, so I can take and debug some of the issues that I'm having with character devices. There's also the Fuji device right here, which this will be the device number for Fuji to take and set things like set the network name, etc. So with that, if we come back over, we'll see that we go ahead, find the DCB, store a copy of it, and we'll use that later to get the length of the data that we receive. Then we take and call network setup. Now, network setup basically just does the first bit of interacting with the FujiNet, which basically in this case sets up a command structure that sends the SSID and the password across. It formats it, puts it on the structure, and then ships it off. Now, EOS write character device, if we take a look at how this particular function is set up, we can go to EOS lib and take a look at it. Let's see, it's an EOS lib here, so it essentially creates a synchronous loop that will start the write to the character device, which sets up the device command block, sets up the buffer, and passes the request off to the 6801 to actually do the I/O request. And at this point, we're sitting and spinning, waiting for something to happen. Anything greater than 80 is essentially meaning it means something has happened. And if we get a 90, if we get a 9, chances are it's a 9B, which means that we've timed out and that we need to retry the request again. The reason that this will essentially time out, and it may time out, this is a long-running I/O operation. And for anything that takes longer than 500 microseconds or so on the AdamNet, the 6801 will say, okay, it's obviously taking care of something, it's not ready to respond. So it will keep sending ready packets until the request is actually ready to go again. So in that case, we basically go, okay, well, it's not ready, done yet. So we go ahead and restart the request and ask for it again until we get something that's in the 80s that's not in the 90s here, which means either one of two possible values, either an 80, which is success or an acknowledgement, or 8 or 88 or 8C, which means it's a non-acknowledgement of some sort. So those values, coincidentally, you can pull from the listings of the 6801 master listings that you can find on the Adam archive. I'm going to take and pull those up right now so you can kind of see what's going on. And if we look at the master listing, we kind of scroll through here. If I can get to it, we'll see some interesting things in the middle of the listing, which this is essentially the MAC, which is the central part of the AdamNet control software, which mediates access control to the device, whether or not the device needs to respond, that sort of thing. Of course, we have the different constants for different message types that we can potentially respond to, but we also have error codes, which start at 80, and you'll see some of them here. If we time out doing a ready, we get an 81, for example, but if we keep going, we'll see that if we send data and we get a non-acknowledgement there, then we get an 88 back as part of our response. There are different types of NACs and things that we can respond to. But if we actually take a look down here, we will see there's a 9B here, which is a timeout error, which is interesting to let us know that, well, we still haven't, the request is still processing, we should try again. So with that, the listings here are invaluable. And they'll actually ultimately be transcoded into the EOS library as defined macros. So write character device, we take and we just keep doing the writes, and depending on if we time out or not, we try it again. So this creates a synchronous loop for us, so we don't have to do this in our main program. We send the function call here to the device with the buffer that we want to send and the length of that buffer, and it will take care of sending it off to the AdamNet for us. And actually, if we take and dig down that bit further, we can go just a bit further here and go into EOS start write character device, for example, and you'll see that it is essentially a call into the appropriate routine inside of EOS. We set up the registers like they need to go, and then we do the ASM call here and return the error code from our bytes A here. Now we can take and refine this a bit more. If the carry flag is set, then we can take and return this as an error code or not. I'm still kind of weighing the pros and cons of doing that. So here we go. So there's that. So in an EOS end write character device. So you'll see at the end of the day, we're essentially just making calls into the system here and getting back, passing in the values that the system calls need, doing the system call and returning back the values that the system calls give back to us. And this forms the basis of EOS lib and the like. So we'll go ahead and close that for right now, and we'll continue. At that point, we're sending a write to the Fuji device, which is essentially starts with this byte right here, followed by 32 bytes, which is the SSID, followed by the password, which is 64 bytes right here. So 96 bytes in all for this particular command. And that is sent off as is to device 0F, which is the Fuji device. Once it hits that, it winds up over here. And we start off by basically anything that comes through the system essentially gets thrown into AdamNet process command. This is called directly from main. So if you actually take and pull into main, you'll see this is actually being called as part of the main loop here, more or less. So we come through, we read the byte of the incoming command, we separate out the device, we go ahead and turn on the LED to indicate that we're processing this, and we look through the daisy chain of our devices. And this is actually set up in setup here. You'll see a call to setup, which actually does all the bits and pieces to connect the devices inside of main itself. Anyway, I'll get back to that in just a minute. Sorry, I'm getting off into the weeds ever so slightly. Point is that we have this daisy chain here that we are essentially using to take and connect our devices together, get everything running. And we figure out, given the device that we peel away from the byte that we just read, if it's for us. If it's not for us and we hit the end of the chain, okay, we wait for idle and wait for the next thing to happen. If we actually take a look at that, then we wind up over here where we implement wait for idle. Now on the 6801s themselves, the 6801s have what they call wake up functionality, which basically waits and listens for 10 zero transitions in a row. It means everything, just nothing but 10 solid zeros all in a row, at which point they assume that the bus is asleep and that it can start listening for a new packet. We can't do that here. The UART for the FujiNet can't do that, so we actually have to implement this in an equivalent functionality, essentially using a timer with microsecond precision. And once we hit approximately 150 microseconds or so, and we don't hear anything, then we assume the bus is pretty much idle and we continue on. At which point we basically come back here, and if this is a device that we actually, if this is a device that we need to pay attention to, if it's in our list, then we take and pass it off to its AdamNet process command with the byte that we just got. Because that byte will tell us the command for that particular packet. So if we take and say, for example, if this is for device F, then it winds up here in Fuji, at which point we get to AdamNet process. And we grab the next byte, which we take and grab that byte, and we figure out the command for that byte, which corresponds to the upper 4 bits, the upper nibble of that byte that we just read. And we match it against one of our constants here, which these correspond to the different constants that you find in the 6801 here. If we got a status command, if we're clear to send, if the Atom is saying it's clear to send, the Atom's asking for a receive, we're sending something to the Atom, for example, or the Atom is saying, are you ready? And those are the main ones that we need to take care of and deal with for this particular device. Now, for example, we can start looking at control status. When we actually take and do, for example, when the Atom first starts up, it does a roll call asking for the devices that are actually available on the system. And we can see that from here. One of the things that we have access to, I have a logic analyzer attached, which I'm using basically to do debugging, and more importantly, I have it looking at the receive and transmit lines here. I also have it looking at the transmit line from the FujiNet itself, from the transmit pin on the FujiNet before it goes into the transistor, so I can see the signal that see what I'm transmitting against what I'm also transmitting and receiving. It shows up in both places for things that I'm transmitting. And we are looking at the reset line. The main reason we're looking at the reset line here for the purposes of logic analysis is so that I know when to start my trace. So anytime that I take and push the reset, I'm looking for the falling edge of that reset pulse. And based on that, we take and start doing the trace here. So bam, bam, the edge falls, goes low, and then we start with the trace. Now, the first thing that the Atom actually tries to do is it tries to look through every single device in the system, essentially doing a roll call, asking status for every single one of these devices. You'll see the first one here. This is for the keyboard. The keyboard is device number 1 on the AdamNet, and we're looking for a status packet, which is 1-1. If a device is present, it will respond within a certain amount of time, usually approximately 100 to 200 microseconds, to take and grab a status call. So in this case, we'll see that we're responding within 200 microseconds here, which is still acceptable. 150 to 200 microseconds, which is acceptable, with a response packet. This is a status response packet, which upper nibble is 8, and then we respond with the maximum size that a receive packet can have. This is also the size that you need to specify when you do the receive in the first place, and you get a status byte, and you also have a reserved byte here and a checksum. If everything looks good here, then what you wind up with, I apologize here. Sorry, I'm thinking a couple things at once. This is actually this is actually the byte that tells whether or not this is a character or a block device. If this is a 0, then it's a character device. If it's a 1, it's a block device. And we'll see the difference between character and block devices in just a moment. Everything's good. We send it off with the checksum. Adam validates the checksum. And if everything's good, we wind up with the Adam basically saying we acknowledge this status request for this device. And the Adam continues on. We have one right here for the printer, which is also a character device. We see one here for 1.3, which is nothing. There's nothing there, so there's no status response. So the Adam just continues onward. No problem here. Now, for this one right here, we have our first mass storage device, which is at device 4. And I'm responding with the fact that this is a block device with a maximum message size of 1024 bytes, 0400. With the appropriate checksum, okay, Adam likes that and continues on. And we continue on and on and on. Here's the one for the tape device. You'll see that we have a tape device with nothing in the tape drive, so we have both 3s for the upper and lower nibble here. Adam's okay with that. 1A, 1B, 1C, 1D, 1E. And here is our temporary network device. This is the temporary network device, 1E. We respond with our status packet here, indicating that this is a character device with a maximum message size of 1024 bytes, 0400. Okay, Adam likes that, no problem there. And finally, we have the FujiNet control device, which basically much the same thing as our temporary network device here. Same packet size, also a character device. And then we continue onward. At which point the Adam will go, okay, we're good. We have all the device control blocks filled in. Everything's good. We can continue on with the boot process. And the first thing that we'll do is we will check the disk status here to make sure that everything is okay for us to start asking for stuff. It's okay. Adam acknowledges that. And then we follow that up with, okay, are you ready? This is a ready packet. If we take a look, we can see ready 00D. Yep, okay, we're good. We acknowledge with an acknowledgement 9.4. Okay. So then, since this is a block device, the read block command will start by doing a send, sending data to the peripheral, in this case, the virtual disk device, asking us for the next 5 bytes will specify the content of our send request. So we have a send request here. How many bytes are in that send request? 5 in this case. And these 4 bytes, in this case, indicate the block number, and the 5th byte is reserved. And the checksum of all of those bytes, content of those bytes is, of course, 9.4 with everything, or sorry, 0. So, okay, good. Peripheral calculates that, says that that's okay. We respond back with an acknowledgement. And the first thing that happens is, okay, great, we're good. Adam does some thinking and says, okay, I want to receive something. I want to receive what I just asked for right here. Bam. We send back an acknowledgement sometime later because it's taking us some time to take and fetch the block from our internal flash. Adam went, okay, that obviously timed out. It took too long. And in this case, that response took approximately 1160 microseconds, which is way too long. So it goes, okay, no problem. We'll ask again. So this is the read block command, essentially doing the ready and say, okay, we'll ask again. Are you ready? Well, in this case, we do answer within the allotted time again, which in this case, we answer that we acknowledge the ready request within 171 microseconds. Okay, good. So it asks for the block again, just to be sure. Since we have it in memory here and we're not having to fetch anything, we pretty much immediately acknowledge that we have the block. 4494 again. And at this point, 449434, we get a request from the Atom that we want to do that it says, okay, clear to send the content of the data. And we respond back with a response packet. This is a send response, starts with a B, and this is for device 4. The length of that response, which is 1024 bytes, and we fill in the contents of that block. Okay, Atom is okay with this. It calculates the checksum, makes sure everything's okay, at which point Atom sends back an acknowledgement, says that that's okay, and the process repeats for the blocks that we're going to load into memory here. At this point, by the time we hit the end here and we have the last acknowledgement, the program that you saw on the screen here is now loaded. At which point, since we're doing an immediate connection to the network and we're not asking for that network, we formed that network request that you saw before over here, connecting to the network. We formed that command, the SSID, and the password. We connect to the network and we write to the character device with the message that we just formed here in S. That culminates into this. And if you'll see here, this is a message with 61 hex bytes in length, which is 96. The FB that you saw right here, which corresponds to the command that we're sending across. And finally, the message, the rest of the message, which in this case contains the SSID, which is 0 terminated and 0 filled, and the password. Again, 0 filled, 0 filled. Sends everything over, checksum calculated. The peripheral acknowledges that we've received that. All is good there. So with that, that gets us to the point where we wind up over here. So we have, we received this send here. It winds up in AdamNet control send. And we have all of these different commands that we can send, which are the first byte in the send packet that we send back. And the one that we send over here is FB, which is set SSID. So when we realize that this is a send packet, the first thing that we do is we immediately grab the 2 bytes for the length, because that's our responsibility to do. And we do the AdamNet receive here, which grabs the command that we're going to get. So FujiNet command send SSID. Let's go to that definition here. And you can see Fuji command set SSID, some debugging information, which winds up in the debug console. And you can see the same data structure that we have defined over here is mirrored over here. We immediately take and receive that whole buffer. This is a convenience function that's in AdamNet CPP here, which basically takes the data that comes across, however many bytes that we ask for. In this case, we're passed in, since this is a variable length send packet here, I pass in the length here so that we can deal with it. Since we already have the command and it's already parsed, I remove that 1 byte from the length here. and grab the rest of the buffer. We then, since the last byte of the send packet is the checksum, we go ahead and receive it. Now, we could actually take and calculate and check against this. I'm not currently doing that here because I'm still working out the timings and everything. But you would basically check the checksum here, and if it's okay, then we take and acknowledge it. If it's not, then we would take and send a non-acknowledgement here. But notice that before I actually do that, I'm waiting a certain amount of time so that I can make sure that the Atom is actually listening for my response. Needs to be at least 80 microseconds, preferably 100 to 150 microseconds. At which point we acknowledge it, we go ahead, we do the command, and then we bounce back into the main loop here. Now, as part of the main loop, because the UART is actively receiving data, because the UART is actively receiving data and actively filling in the input buffer here, it is important that as we're doing certain things, we need to ignore anything that might be coming across, because we might be seeing ready packets and things that have already expired that we do not need to respond to. If we don't, essentially, we'll get the data that has piled up in our input buffer and cause race conditions on the AdamNet, either in the form of network contention or in confused network state. So it's important for us to take and flush the input, discard anything in the input buffer, and go from that point. At the end of the day, this is essentially how we send commands to the Atom using to the FujiNet using send packets. When we take and do a character write, they wind up as send packets. They get processed here. For anything that has a response, we need to basically take and formulate that response so that when the Atom takes and deals with it and asks for it, we can send it back. An example of this would be the get SSID command. We can see right here, conversely, get SSID. We get the checksum. There's no parameters, so the only thing that's part of this here is we say the command byte, we grab it, pull it back, okay, grab the checksum, and we're basically done. Okay, great. At which point we take and get the SSID from the FujiNet, we delay a certain amount of time, and then we send an acknowledgement indicating that this is finished. And this should actually be 150. So once we've done that, the Atom, if we take and do we need to take and get and receive the data using read character device. And anything that happens there, we essentially do a receive. We start with the receive here. So say, okay, receive. Okay, we'll go ahead and acknowledge it because the response has already been put into the response buffer, which will cause a clear to send. And if we look at clear to send, we'll see that we send a response packet with the response length, send the buffer over, and then we immediately clear out the response buffer and set it up again so that everything's nice and clean for the next operation. And that's essentially it. We're bouncing back and forth. We're sending commands. We're getting responses back. So that brings us back over here to the Atom here. Done. Okay, great. Now at this point, we come back here. We've done network. We ask for the host name. We ask for the port. We take and convert the string here to an integer, no problem. Then we do the connect. If we look at connect, we'll see that we are setting up a command here, another data structure for the command For the target port that we want to put in here, we put this at the first because it's really easy to take and strip this off and assume that the rest of the packet is the host name that we want to connect to. Just makes it easier to process. And we set up the command, which is FF on device E here. This is just temporary as an example. Set the port, copy the string into place. We write the character device here, and that culminates in a connected response here, which if we take and zoom out a little bit, we'll see first thing and foremost, we're doing some things here. A common pattern that you will see throughout AdamNet is things like scanning the keyboard, where we look for a character device. We say, receive from the keyboard. The keyboard doesn't have anything to send, so it immediately takes and sends a non-acknowledgement back. And this just repeats as it scans the keyboard here. And as you can see, as we start typing characters in on the keyboard, in this case, we do have something to send back. So the keyboard sends an acknowledgement. Adam sends a clear to send. And this culminates in a send response packet, which contains the character, the one character of the key press to send. Continue on. And so that's just me typing in bbsfoztext.com. And actually, if we take a look, we can actually see, if I take and open up the binary decoder output view, we'll actually start to see, once I scroll down past this, you'll start to see bits and pieces of things being typed in on the keyboard. See? Bam, 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 and so on. You can see the network, all the different things being decoded here. We'll put this off to the side for a minute. So there we go. I finish entering in all the data, and we immediately take and send off the connection request. The write command immediately formulates into a ready here with an acknowledgement, with a send packet containing the 256 bytes of the host name. And we get that. We're okay with it, so we acknowledge it. Adam's okay. And so from this point on, we're connected, and we start looking for data from the, once we're ready. If we're not ready to take and respond to certain things, you'll see that we're just kind of like, okay, nothing's happening. The 6801 will go, okay, so nothing happens. So we can choose to keep hammering it to wait for data or not. That's our choice. So that brings us essentially to connected, and at that point, we drop right into the terminal program, where we basically find ourselves in a never-ending loop to deal with the keyboard and then deal with the terminal. Dealing with the keyboard is simple enough. We actually take and use since we prime starting keyboard scanning already here, we're already set up to start reading the keyboard asynchronously. And we do this so that we can keep running in a loop and not get stuck waiting for key presses. So we go ahead, see if there's anything available on the keyboard, and if there is, we immediately set up the second command that the E device can actually respond to, which is FE, which means send information. That becomes, the second byte of that packet becomes the key press that we send in. We send that off, we clear everything off, clear off the key presses, and start to read the keyboard again while we fall down into the display. Now, all we're doing here with the FE command, if we actually take a look at that from here, we can go into network CPP for our temporary network device. And we can see our two commands here for command connect and Command Send. If we look, again, it's the same pattern. We take and receive the, we go ahead and we've already received the length and response, clear everything off. And then we form our message here. It winds up, we're reusing essentially the response buffer here for our own purposes, because why not? These commands come in synchronously in sync, so we can reuse memory where we need to, and we really need to on the ESP32 because memory is in short supply. We go ahead and we receive it. Okay, we received it. We wait a moment and send the acknowledgement. Now you notice that the acknowledgement for this guy is 9E. This is because it is device E here. And then we write out the response to the TCP socket. And that's the implementation of the send command. And I do apologize because I did accidentally skip over the connect, how connect is implemented, but you'll see that connect is really simple. All we're doing for connect is grabbing the host name, getting the port from the host name real quick, removing it from the total message size here so we can receive the buffer, however big it happens to be, and grab it, grab the checksum, wait for a minute, acknowledge that we got it, and then we take and connect using the TCP client object that's part of FujiNet here. Now we have a flag right here. If this is already connected, then we just simply take and return. We're done here. We don't need to do any further processing. But I have a flag here which is called already doing something, which makes sure that if we've run this before, that we don't accidentally take and try to reconnect again. This gets set first time through so that we don't accidentally try to reconnect each time if and when the command most likely times out. The other side of this is essentially the term display command. And this solely relies on the fact that this device is so simple that we assume that any receives have to deal with data coming in from the outside TCP socket. We just assume that from the get-go. So we take and read, they read from the character device. And when we read from the character device, the size of that response has to be the same size as what is responded to in the status. We say in the status the maximum message size is 1024 bytes. That means that the length of our receive also has to be 1024 bytes, which means that we need a variable that's at least 1024 bytes in size, which in this case is response, to hold that maximum size of that response. If this value isn't, if the length value isn't the same size as what you report in the status, the receive command is ignored by the master 6801 and you don't get your receive. It just doesn't happen. So at this point, we read from the character device and we get the error code that comes back. In this case, if we get an 8-0, that means we got some data back and we acknowledge. And since we've already gotten the DCB early on in the program, it's still there. It hasn't moved. It stays there until everything gets reinitialized. We can immediately take and peel through, looking at the DCB, looking for the length of what was just passed to us. And for each character that's passed through us, we take and iterate through response, outputting the result. So that's essentially how this works, and it keeps repeating this over and over and over again. So that brings us back here. I know. I've been talking nonstop. And how long have I been going on here? Just rambling on incessantly. Oh, 45 minutes. So you kind of see we're still stuck very much here. It just stopped responding. And if we take and do a logic trace here, we'll actually start to see what's going on here. In fact, let's go ahead and do that. We'll take and resize, make sure everything's good. I will take and hit the stop. I will take and start a trace here. I'm going to reset my ESP32 to make sure that everything is okay. And actually, for the sake of illustration, I'm going to bring up the monitoring here. We're going to bring up a monitor window. And we'll make it full screen here so that we can see what's going on. Wait for this to come completely up. Come on. Oh, wait. I'll just hear bang. There we go. Let's just reset that. Okay, we're good. We can see our FujiNet here coming up completely, adding device 4 for our mass storage, our temporary network device, and our FujiNet control device. And the temporary network adapter is started up. We have about 4 megabytes of heap that is currently available for our use at this point. And setup is completely finished in about 425 milliseconds. So with that, we'll go ahead and do a reset here. Bam, okay. So now we've got this going here, and you'll see that the trace has actually started. And we'll go ahead and try again. Connected, and you'll start to see data come across. And you'll see that we actually kind of get most of the way here. It's just we seem to have some slight synchronization issues. Not exactly sure what could be happening here, but I will figure it out. And I would love to get some help from other intrepid people to see if we can figure out what could be happening here. You'll see it's acting a bit better this time. But here we go. So, yep, boom. We're done. We hit stop, and we can kind of see the various bits of interaction. As we see data coming in, this is data coming into in from the TCP socket versus keyboard interactions. More network information, just slowly eking through. I'm trying to think. I'm trying to find some nice little bits of keyboard information here. Is there? I don't know. But you can kind of see, I'll actually take and put this trace right here so we can see what could be happening here. I'll take and save this actually as part of the session, so that we all can take a look at this together, maybe get some insight. This is the excellent Pulse View program. You can get it as part of the SIGROC project. Easy enough to download and use. But you can see bits and pieces of data coming in and off the network. If we take and look at the binary decoder, we can see that the data is coming through. I find it funny that because we're scanning and non-acknowledging both the network and the keyboard here, we see nana, 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 nana. But, you know, that's pretty funny. So you see bits and pieces of keyboard, you see the network data come through. So far, sometimes it works really well, sometimes not. So this is purely a timing issue that needs to be worked through. And this is what I'm trying to work through. Help, as always, would be most appreciative. It's one of the reasons why I made this video here, so I could fully explain what's going on. And if you guys want to help, you know, more power to you guys. I would really appreciate the help. So I'm basically going to leave the video here and take and encode it so you guys can see what's going on. So until next time, guys, hopefully we'll get this dealt with. Have fun.